Did you know time isn't the same for everyone? It sounds strange, doesn't it? We're used to time ticking by at a steady pace, marking our days and years, but the universe has a few tricks up its sleeve. It turns out that time, as we experience it, is not a constant. It's a relative concept that can be influenced by gravity and speed. This mind-bending phenomenon is called time dilation. Imagine yourself standing still on Earth watching a friend zoom off in a spaceship. Now, imagine your friend's spaceship approaching the speed of light. As your friend travels faster and faster, something incredible happens. Time itself slows down for them relative to you on Earth. Time dilation is one of the most fascinating and counterintuitive consequences of Einstein's theory of relativity. It tells us that time is not a rigid, unchanging backdrop to the universe, but rather a fluid and dynamic entity that is intimately connected to the fabric of spacetime. In the vast expanse of the cosmos, near objects of immense gravity like black holes, time dilation becomes even more pronounced, leading to scenarios that seem straight out of science fiction. Let's dive deeper into the mysteries of time dilation and explore how it plays out near these cosmic behemoths. Before Einstein, physicists believed that time was absolute and universal. They thought time flowed at the same rate for everyone, everywhere. However, Einstein's groundbreaking theory of relativity shattered this long-held belief. He showed that time is not absolute but is relative to the observer's frame of reference. Imagine two clocks, one placed on Earth and the other on a high-speed spaceship traveling close to the speed of light. Einstein's theory predicts that the clock on the spaceship will run slower than the clock on Earth. This difference in timekeeping is not due to any mechanical malfunction of the clocks, but rather a fundamental property of time itself. Einstein proposed that time and space are not separate entities but are interwoven into a single fabric called spacetime. Massive objects like stars and planets warp this fabric, much like a bowling ball placed on a trampoline stretches the fabric around it. This warping of spacetime is what we experience as gravity. The stronger the gravity, the more spacetime is warped and the slower time runs. This is why time slows down near massive objects, a phenomenon known as gravitational time dilation. Black holes, with their immense gravitational pull, provide the most extreme examples of time dilation in the universe. One of the most famous thought experiments illustrating time dilation is the twin paradox. Imagine two identical twins, let's call them Alice and Bob. Alice stays on Earth while Bob boards a spaceship and embarks on a high-speed journey to a distant star. Bob's spaceship travels at a significant fraction of the speed of light. According to Einstein's theory of relativity, time slows down for Bob relative to Alice. This means that Bob ages slower than Alice. When Bob returns to Earth after his journey, he finds that Alice has aged significantly more than he has. This difference in aging is a direct consequence of time dilation. The twin paradox highlights the bizarre and counterintuitive nature of time dilation. The twin paradox is not just a theoretical concept, it has been experimentally verified using atomic clocks. In one experiment, two atomic clocks were synchronized and one was flown around the world on a jet. When the clocks were reunited, the clock that had traveled on the jet showed a slightly slower time, confirming Einstein's predictions. The implications of the twin paradox are profound. It suggests that time travel, in a sense, is possible. By traveling at high speeds or experiencing strong gravitational fields, we can effectively travel into the future. As we approach the speed of light, time dilation becomes increasingly pronounced. At everyday speeds, the effects of time dilation are negligible. However, at speeds approaching the speed of light, time dilation becomes a dominant factor. Imagine a spaceship traveling at 99% the speed of light. For every year that passes for an observer on Earth, only about 7 weeks would pass for the astronauts on board the spaceship. This means that the astronauts would age 7 times slower than their counterparts on Earth. At the speed of light, time dilation becomes infinite. This means that time would essentially stop for an object traveling at the speed of light. Of course, no object with mass can travel at the speed of light, so this is a theoretical limit. The speed of light acts as a cosmic speed limit, preventing any information or object from traveling faster than it. As an object approaches the speed of light, its mass increases infinitely, making it impossible to reach the speed of light. Time dilation at high speeds has been observed in particle accelerators, where subatomic particles are accelerated to near-light speeds. These experiments have confirmed that time dilation occurs as predicted by Einstein's theory of relativity. Section 5. Gravity's grip on time, black holes, and time dilation. Gravity has a profound effect on time, especially near massive objects like black holes. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape. As we move closer to a black hole, the gravitational pull becomes increasingly intense. This intense gravity warps space-time to an extreme degree, causing time to slow down significantly. Imagine two clocks, one placed far away from a black hole and the other placed near its event horizon, the point of no return beyond which nothing can escape the black hole's gravitational pull. The clock near the event horizon would run much slower than the clock far away. If we could observe a clock falling into a black hole, we would see something truly remarkable. As the clock approaches the event horizon, we would see its ticking slow down, eventually appearing to freeze in time. This is because the light from the clock is struggling to escape the black hole's intense gravity. Time dilation near black holes is one of the most mind-bending consequences of Einstein's theory of relativity. It suggests that time is not a constant but rather a fluid and dynamic entity that is intimately connected to gravity. Section 6. The Singularity, where time stands still. At the center of a black hole lies a point of infinite density and gravity called the singularity. According to our current understanding of physics, the singularity is a point where the laws of physics as we know them break down. Time dilation near the singularity becomes extreme. As we approach the singularity, time slows down infinitely. This means that from the perspective of an outside observer, time would essentially stop at the singularity. What happens inside the singularity is a mystery. Some theories suggest that the singularity is a point where all matter is compressed into an infinitely small point. Others propose that the singularity is a gateway to other universes or dimensions. The singularity remains one of the greatest mysteries of modern physics. It is a place where our current understanding of the universe breaks down, and new theories are needed to explain what happens at this point of infinite density and gravity. Time dilation near black holes and the singularity challenges our fundamental understanding of time. It suggests that time is not a rigid and unchanging backdrop to the universe, but rather a flexible and dynamic entity that is intimately connected to gravity. Section 7. The flexible fabric of time, a cosmic tapestry. Time, as we've discovered, is not a rigid framework that governs the cosmos. Instead, it's a flexible fabric, woven into the very essence of space-time. This fabric can be stretched and squeezed, its rhythm quickening or slowing depending on the cosmic dance of gravity and motion. We've journeyed from the familiar ticking of clocks on Earth to the mind-boggling time warps near black holes. We've seen how speed can propel us into the future, at least from a stationary observer's point of view, and we've peered into the enigmatic heart of a black hole, where time seems to lose all meaning. These explorations have revealed that time is not the absolute, unwavering entity we once thought it to be. Instead, it's a dynamic player in the cosmic drama, responding to the presence of mass and the rush of motion. Time, it turns out, is relative. This realization has profound implications for our understanding of the universe and our place within it. It opens up tantalizing possibilities, hinting at time travel scenarios and challenging our perception of reality itself. Section 8. A black hole rendezvous. Would you dare to travel through time? Imagine for a moment that you could journey to the edge of a black hole, a cosmic abyss where time itself seems to bend to its will. As you approach this gravitational behemoth, you'd witness the universe around you aging at an accelerated pace. Stars would explode and reform before your eyes, galaxies would dance through the cosmos in a breathtaking celestial ballet. But what about you? Time, for you, would slow to a crawl. Years might pass for the outside universe, while you experience only a fleeting moment. You would be a time traveler, venturing into the future, leaving behind everything you know. It's a captivating thought, isn't it? But it also raises profound questions. What would it mean to exist outside the flow of time as we know it? Would we retain our sense of self, our memories, our connections to the world we left behind? These are questions that science alone cannot answer. They delve into the realms of philosophy, of our understanding of consciousness and existence itself. But one thing is certain, the exploration of time dilation, particularly near black holes, forces us to confront the limits of our knowledge and the profound mysteries that still lie hidden within the fabric of the universe. Would you take the plunge, knowing that time, for you, would never be the same?